Welcome back, everyone. We are starting a new unit called Thermochemistry. In this lesson, we will talk about the heating and the cooling curve. Before we get started on the heating and the cooling curve, there's a little bit of vocab that you must know before we get started. So please feel free to pause this video and read over the vocab. We have the definition for a temperature, kinetic energy, potential energy. Higher temperature means that you're going to have more kinetic energy. Lower temperature means that you're going to have less kinetic energy. And thermal energy or heat flows from higher temperatures to lower temperatures. Let's get started. Now here we have a heating curve. This heating curve is already labeled for you. Here we have at the beginning from A to B colored purple. This is the solid. From B to C, the substance that we're talking about is now melting. So it's going from a solid to a liquid. From C to D, it is now a liquid. From D to E, the liquid is now boiling and becoming a gas. So liquid to gas. And then from E to F, the substance is a gas. So we have one phase change that is jumping from solid to gas. So it goes from a solid directly to a gas, and that is called sublimation. Now, the reason that this is called a heating curve is because point A starts at a low temperature. And point F, if we follow it to the y-axis, ends at a high temperature. So here we see that the temperature is going up. Now, temperature is directly proportional to average kinetic energy. So as temperature goes up, the average kinetic energy also goes up. So overall, the heating curve, we see that the energy is increasing. It's going up as you go from point A to point F. So we can say that the heat overall in this curve is being added or being absorbed. Now let's talk about each individual line here of in terms of energy, how is it changing? The two energies that we're going to talk about is kinetic energy and potential energy. Now from point A to point B, the temperature is increasing. Point B ends there. So from A to B, the temperature increased. Once again, temperature is a measure of average kinetic energy. So if the temperature is increasing, that means that the kinetic energy is increasing. So what happens to the potential energy? Well, one thing you need to know is that when one energy is changing, the other energy is staying constant or staying the same. So in this case, from A to B, the kinetic energy is increasing, so this is changing, so the potential energy will remain constant. And I'm just going to put a line here, and that will represent that it stays constant or stays the same. Now let's go to line BC. Here we see that from line B to C, the temperature has not changed. It is only at one temperature, which is right here. I don't know what temperature it is, but all I see is a flat line, and I see that the temperature is not changing. So in this case, the temperature is staying constant, so the average kinetic energy is staying constant or staying the same. Now, when we discussed this curve at the beginning, we said from point A to point F, the energy overall is being added or being absorbed. the heat overall is being added or being absorbed. So that means that overall in this graph, we see that the energy is increasing. So from B to C, the kinetic energy is staying constant, so the potential energy is going to be increasing. Now that we have these two lines labeled, we can fill out the rest. So here we have C to D, where this substance is in the liquid phase. Once again, we see something that is on a positive slope. We're starting from this temperature and going up to this temperature. The temperature is increasing once again, so the kinetic energy is increasing. Now, once again, going back to what was mentioned earlier, one changes, the other one stays the same. So one energy changes, the other one is staying the same. Let's go to DE. When this substance is boiling, it is at one temperature. That means that, well, the temperature is staying constant, so the kinetic energy is staying constant. If we go to the y-axis, this is the boiling is happening at one temperature. The boiling point is at one temperature. Now that means that the potential energy must be the one that is changing, and it's going to be increasing. Last one for gas. The kinetic energy, while the temperature is increasing from point E to F, so the kinetic energy is increasing and the potential energy is staying constant. Now we should see a pattern here. On the slopes, so I'm going to circle that, on the slopes, we see that the kinetic energy is increasing and the potential energy is remaining constant. And on the flat lines, the kinetic energy is staying constant and the potential energy is increasing. All right, so let's see, how would we get a heating curve question being asked to us? Let's look at this one. What is the melting point of this sample and the total time required to completely melt the sample after it has reached its melting point? So it wants to know what is the melting point, and then what is the total time for this to melt. Okay, let's see. Well, this is a heating curve, so I'm just going to quickly label this graph. I'm going to do this quickly by using an abbreviation. So S for solid, L for liquid, and G for gas. Okay, so I know that the first slope, positive slope, is going to be solid. The second one is liquid. The third one is gas. They're asking me for the melting point. Well, melting, that is going to be between the solid and the liquid. So this is my melting point. At this point, I don't want to concentrate on anything else. I'm just going to look at this. So the first thing they want to know is, what is the melting point? Well, the melting point is happening here. If I connect this to the y-axis, it's at here. So the melting point for this would be 50 degrees. So the melting point at 50 degrees Celsius. Now it says, what is the total time it takes to melt this sample? Well, the first 2 minutes over here, the sample is a solid. So we cannot include this in the time that this sample melted, because the first 2 minutes, this sample was a solid. It started to melt at minute 2, and then it stopped melting at minute 5, because after minute 5 it was now in the liquid phase. So now how long did this take to melt? Well, we can count 1, 2, 3 minutes. Or we can do 5 minus 2 and we would get the same answer of 3 minutes. Let's move on to the next. What is the total length of time that the solid and liquid phase existed? Okay, solid and liquid phase existed. All right, well, solid and liquid phase existed. That would be in between the solid and the liquid phase. So here we have the first slope solid, second slope liquid. When was solid phase existed with liquid phase? That would be here, when it's melting, when it's going from the solid to the liquid phase. So what is the total amount of time? Well, it started to melt at minute 2, and it finished melting at minute 6. So once again, we can either do this or we can subtract it, which is 6 minus 2 would give us 4 minutes. All right, let's go to the next. Which line segment of the graph represents boiling? Okay, so here, once again, at this point, it should take me a couple of seconds to label these. So we got a solid, we got a liquid, and we got a gas. Which line segment represents boiling? Well, boiling is going to happen in between the liquid and the gas. So it'll be right here. So what line segment would that be? That would be D, E. All right, let's go to the next one, which is the cooling curve. Once again, here I have it labeled. Now the cooling curve, it's called a cooling curve because you're starting a substance from the gas phase, so at point A, and then you're ending all the way in the solid phase. And the temperature is dropping, so we are at a high temperature, and then we end at a low temperature, so it's going down. The temperature is going down. Well, if the temperature is going down, that means that the average kinetic energy is going down throughout this graph. So I can say, okay, well, in terms of heat, what is happening to the heat? If the temperature is going down throughout this graph, the heat must be released. So let's go into how does the energy change throughout this graph. Let's go from A to B. From A to B, I see a decrease in temperature. It starts all the way here at a high temperature, A, and then B goes to a lower temperature. So that means that the temperature is decreasing, so the kinetic energy must be decreasing. Going back to if one energy is changing, the other one is remaining constant, the potential energy is staying constant here. Now let's go to line BC. This is at only one temperature, and this would be that the kinetic energy is constant because it's not changing. The temperature is not changing. So that would mean that the potential energy is decreasing. Once again, the reason that it's decreasing is because, well, overall, throughout this graph, the temperature is decreasing, so the energy is decreasing overall. If we go to the next one, CD, the temperature once again is decreasing. It's going down. So kinetic energy is decreasing. Potential energy is remaining constant. Going to the freezing point from liquid to solid. This is at one temperature, so the kinetic energy is constant and the potential energy is decreasing. And the last one, EF, the solid. Once again, temperature is decreasing, so the kinetic energy is decreasing and the potential energy is remaining constant. We should see a pattern. We see that when this substance is a gas, when it's a liquid, and when it's a solid. When it's a gas, a liquid, or a solid, the kinetic energy is decreasing while the potential energy is remaining constant. And then we have when this substance is going through phase changes, like condensation and freezing, the kinetic energy is remaining constant and the potential energy is decreasing. Overall, the energy of this cooling curve is decreasing, so we can say that the heat is being released throughout this process. And now we have a phase change that is called deposition. That is when the gas becomes a solid. So how would we be asked questions of the cooling curve? Let's take a look at this one. What happens to the potential energy and average kinetic energy during CD? So I'm going to circle CD. Well, I see at point C, I'm at 150, and point D, I'm at 90. So the temperature dropped. This is telling me, okay, if the temperature dropped, that means that the average kinetic energy is decreasing. So when one energy is changing, the other one is staying constant. So for this, if the average kinetic energy is the one that's changing, it's decreasing, the potential energy is the one that's staying constant or remaining the same. Now, for the next one, it says, what happens to the potential energy and the average kinetic energy of the molecules in DE? So now we're at DE, the following line. In DE, I see that the temperature is not changing. It's at 90. So if the temperature is staying constant, that means that the average kinetic energy must be constant during DE, and the potential energy must be decreasing because this is a cooling curve. Let's go to the next one. Determine the number of minutes that the substance was in the liquid phase. Liquid phase. Okay, so we got to do a little bit of labeling. From A to B, this is at a very high temperature. Look, A is all the way up here. So we're at a very high temperature. This is starting at a gas phase. Then the next negative slope is a liquid, and then we have a solid. So when is this liquid? It is throughout CD. They're asking you the number of minutes that it was a liquid only. They don't want to know about anything else, just the time that it was a liquid. So I see that from time 6 to time 11, this substance was a liquid. So what I could do is I could just take the difference of those two numbers, 11 minus 6, and we get 5 minutes. All right, let's keep going. So here we have a multiple choice. It says, at standard pressure during physical change, does the potential energy decrease? So when does the potential energy decrease? Okay, we have two options here. This is a multiple choice. We have to know which curve we're going to think about if we're talking about something decreasing. You have two options, either the heating or the cooling curve. We just went through both of them. The heating curve, we talked about point A is all the way down here and it stops at point F, which is like around here. So from A all the way to F, we can say the overall, the energy is being added, it's being absorbed. So this will not be the curve that we're talking about if we're looking for something that is decreasing. So heating is out. The cooling curve is the one that we should think of if they're asking us for an energy that is decreasing. Because for the heating curve, there's two options. Either one of the energies is remaining constant or increasing. And for the cooling curve, either one of the energies is staying constant or decreasing. So the two options for heating, increase or constant. That's what is happening to the energy in a heating curve. In a cooling curve, it's either it's decreasing or it's constant. Since the question is asking us for the potential energy decreasing, that is our key word here to tell us that we are talking about a cooling curve. So let's see our options. It says liquid to gas phase. Liquid to gas phase, that would be boiling, and that would be here, which is not good because we're talking about a cooling curve, not a heating curve. So this one is out. Liquid to solid. Liquid to solid, that is, in other words, freezing. And that is happening here. Liquid to solid, freeze. And here, DE, this is at only one temperature, so that means that the average kinetic energy is constant here. And the potential energy is the one that is decreasing. So this is my answer. Just to go through them to see that these are not the correct answers. C says solid to gas. Solid to gas, that is called sublimation, and that is found on the heating curve, which is what we don't want to use for this question. And then we have a solid to liquid, which is melt, once again on the heating curve. So that's why we are going to rule that out. Our answer choice is B. Now that we did both the heating and the cooling curves, I want to mention some helpful tips that apply to both heating and cooling curves. If you look back, the slopes represent only one phase. So it's either a solid, a liquid, or a gas. It only represents a phase. So for the heating curve, for instance, it's solid, liquid, gas. Over here was gas, liquid, solid. And then the flat lines is where the phase change occurs. So for instance, the first flat line in a heating curve is melt. The second one is boil. So melt is solid to liquid. Boil is liquid to gas. And then for the cooling curve, we have condensation, which is a gas to a liquid. And then we have the second phase change, which is a liquid to a solid, which is freezing. So the flat lines are where a phase change happens. Then we have, if one energy is changing, the other one stays constant. So I'll do an example. For CD, okay, the temperature is increasing, right? So the kinetic energy here is increasing because temperature and kinetic energy are proportional to one another. And the potential energy is constant.